Swayam Prabha. Digital India. Educated India.
Good morning everyone. Welcome to this introduction to electronics class. Today we are going to discuss common emitter mode of bipolar junction transistor. But before going into the detail of CE mode, CE configuration, let's recapitulate whatever we have discussed as far as the common base configuration is concerned. So as I mentioned in yesterday's class, this is the typical common base configuration where you have base in between emitter and base in between emitter and collector. So base is grounded and base is common between input and output. Okay, so that is why it is called common base configuration. And we have discussed two characteristics. One was input characteristics, which is nothing but plot between input current, that is IE, okay, and input so IE and input voltage VBE. Okay, so input voltage VBE. So if we plot that, we will discuss that we will get a exponential plot between current and voltage, because it is nothing but a forward bias PN junction. Okay, and we have also mentioned that if we increase the collector base voltage, okay, so higher the collector base voltage, higher will be the emitter current, simply because with increasing collector base voltage the effective base width will decrease. Okay, so more and more electron in this case will be able to cross base region and will be able to reach to the collector region. So collector current, that is emitter current, is going to increase. Okay, now we have also discussed yesterday output characteristics of the BJT in this common base configuration, where we mentioned there are three regions. One is forward active region or active region, which is basically where the base emitter junction is forward bias and base collector junction is reverse bias. Okay, so apart from active region, there is also saturation region, where both these base emitter and base collector junction is in the forward bias, and in the cutoff region the BE junction is off and base collector junction is reverse bias. Okay, so we have got these characteristics, and I mentioned in the last class that here IC depends on of course VBE, that is basically IC depends on these IEs, okay, different IEs. So if you increase your emitter current, obviously your collector current is going to increase, but it is independent of collector base voltage, because this is a reverse bias, right? So we have seen yesterday in our discussion that in case of PN junction diode, if this is the current and this is the voltage, the reverse bias current doesn't depends on this voltage, okay, this voltage, and it basically a reverse saturation current if there is no there is very little amount of minority carrier, and if we manage to increase the minority carriers, the current will increase. Nevertheless, this current doesn't depends on the reverse bias voltage, that is VCB in this case, right? So this VCB, even if you increase the current, collector current will remain the same, and collector current will only increase if we manage to increase the emitter current, because that will give you more number of carriers in the collector region from the emitter region through base. Okay, so this part we have discussed elaborately in our last class. We have also mentioned there are dynamic input resistance you can define from this input characteristics, okay, from this slope. you can define dynamic input resistance, which is nothing but del VB over del IE for a constant VCB. Okay, because for any particular IE VB curve, VCB is constant. Okay, now dynamic output resistance similarly also you can find out from the slope here. Okay, and this slope, from this slope you see that R naught will be very high, because R naught is hardly changing. IC is hardly changing with VCB, that we have already discussed, right? So this R naught will be very large, and it is the way we define it is basically R naught is delta VCB over delta IC at a constant value of I, because for a particular value of I we can calculate this R naught. Okay, that is the output resistance or dynamic output resistance. What about current gain? In this particular mode, current gain is alpha, which is close to 1, that we have also we have also discussed, and that is alpha IC over IE, and IC is little bit less than IE because some carrier will recombine at the base while they are going to the collector. Okay, so alpha is little bit less than 1, and it is defined as IC over I. So these definitions I forgot to mention in the last class, so we know this now. Now one more thing I want to mention. So this part we have already discussed. Now one thing I forgot to mention in the last class, that is a thing called breakdown. Okay, so if we keep on increasing VCB, what will happen? At some point the transistor will break. Okay, this is same. This is similar like if we increase the let me clean the side, it will be easier. So if we keep on increasing the reverse bias, we know what happens for a PN junction, right? Sorry. Yeah. So if we keep on increasing reverse bias, okay, of a PN junction, then what happens? This is reverse leakage current, okay, or reverse saturation current, and after a certain increase in this reverse bias voltage, the breakdown occurs. You remember we have discussed Jenner breakdown and avalanche breakdown for PN junction discussion. This is the same thing can occur also in a BJT, because this collector base junction is in reverse bias, and if we keep on increasing the collector base junction, at some point breakdown will occur, and this, if you keep on increasing, this breakdown will occur, that is current will increase heavily, okay, all of a sudden. So this is basically your breakdown voltage. Okay, now if you keep on increasing your IE, the breakdown will occur little bit earlier. Okay, this is easy to explain. So as I mentioned, breakdown occurs at large value of VCB, often designate as BVCBO. Okay, breakdown voltage between collector and base. Now for increasing I, as I mentioned, breakdown is occurring earlier, that is lower value of VCB, that is I have plotted here, I have shown here. You see VCB decreases, the breakdown voltage decreases if we go on higher value of I. Why this is the case? Because higher value of I means much larger number of carrier, right? So this larger number of carriers flowing across the junction initiates the avalanche process at somewhat lower voltage. Okay, which is obvious. Now what about leakage current? Okay, leakage current, as I mentioned, leakage current is there in any PN junction when it is in reverse bias. Okay, this leakage current that is exist between base and collector, because because we have reverse bias this junction. Okay, so there is a leakage current. Why this leakage current? Leakage current occurs because electrons are there as a minority carrier in the p base region. These electrons will be attracted by this positive terminal of the battery and negative terminal of the battery, and there are holes in the collector because this is n region. So there are holes, minority carrier holes. They will be attracted and come to base because of this negative terminal of the battery. So this gives rise to a leakage current, which is as I have drawn already in a PN junction diode, there is reverse leakage current, right, or reverse saturation current. So this leakage current is known as ICBO, is a collector leakage current, and this occurs due to the reverse bias of the collector base junction, as I am showing here. Okay, this is our ICBO. Now this ICBO is obviously in the same direction of IC, but it will it will be visible if IE is equal to 0. You see, if there is no electron flowing from emitter to base, which will ultimately go to the collector, then we will see basically IC. But if we reduce this current, or if we make this current to 0, that is we don't forward bias this base emitter junction. Okay, in that case what will happen, in that case there will be this leakage current, which is simply because of this reverse bias. Okay, and this leakage current is known as ICBO, or collector leakage current, right? But you need to remember this direction of current is same as the direction of IC. That is, we already know these are all ICs, right? If we increase IE, we will get ICs, right? Now we go to our common emitter configuration discussion. This is a typical common emitter circuit. Okay, here you see emitter is grounded and emitter is common. Emitter is in between this input and output. Okay, so input is at a base and output is at the collector. So emitter is common between input and output, that is base and collector, and emitter is grounded. That is why this is known as CE configuration. Okay, emitter terminal is of the transistor will be common between input and output terminals. Now if you look carefully, there are these two voltage sources. One is VBB, okay, to forward bias this base emitter junction, and one is VCC, which will ensure to reverse bias this BC junction. Okay, there are resistors RB and RC, which will basically control the amount of current flowing through this device. Okay, so there will be voltage drop across RB and RC, and rest of the voltage will be across these junctions. Now how I am going to ensure that this base collector junction is reverse bias? You remember for majority of our application, or for amplifier application, we mentioned that BJT base emitter junction is forward bias and base collector junction is reverse bias. Okay, so base collector junction is reverse bias. It is pretty straightforward in this diagram here. Why? Because we are applying positive terminal to N and negative terminal to P. So positive terminal is connected to collector and negative terminal is connected to P type base. So that is why it is base collector junction is reverse bias. Okay, what about here? Here you see the supply voltage is connected between collector. Here in this supply case, this supply voltage is connected between collector and emitter. You see, so negative terminal is connected to emitter and positive terminal is connected to collector. So we need to figure out how this base collector junction is reverse bias. Base emitter junction, there is no issues, because if this, you see, positive terminal is through this resistor is connected to P and negative terminal is connected to N. Okay, so you see this is forward bias if the voltage is sufficiently large so that the voltage drop here is more than nearly equal to 0.7 volt. Okay, so this this base emitter junction is forward bias, it is easily visible. What about base collector junction? How we are going to ensure this base collector junction is reverse bias? We can ensure that if the voltage here, okay, if the voltage here, let me clean this. Sorry. Yeah. So how I am going to ensure that this is in the reverse bias? Say this is voltage here is say this is the point Y and this is the point X. Okay. So if Vy greater than equal to Vx, then we can say this is reverse bias, right? If Vy is more than voltage here is more than that of voltage here, then we can say this collector base junction is reverse bias, because this is N and this is P. So N will be connected to higher voltage compared to that of P. So that way this PN junction or this collector base junction will be reverse bias if this condition is maintained, right? Now let's discuss our input characteristics and output characteristics of this particular configuration. Here we are plotting IB versus VB. So IB is the input current and VB is the base emitter voltage. So here also this will be exponential plot, because this PN junction is forward bias, right? And I have plotted this for two values of VCE. So collector emitter voltage, two values of VCE or two values of VY. So VY is nothing but voltage between collector emitter, right? Because emitter is grounded, so this voltage here is with respect to this ground, so VCE. So this VCE, you see, with increasing VCE, your base current decreases. Okay, so you see here, so base current decreases, right? So this is for VCE1, this is for VCE2. Why this base current decreases? This is we have discussed before. So you remember in the last class we have discussed that so this is our base and this is our collector. Okay, and we have reverse bias it. So say this is VCE1. Okay, sorry. So say this is VCE1. Now that creates a depletion region at the base and the collector, right? Now I have increased VCE1 to VCE2. Okay, now if it is VCE2, what happens? The depletion region increases. Why the depletion region will increase? Because the reason depletion region increases because VCE2 is more than VCE1. So here this Vy will be much more compared to Vx, you see, because we haven't changed VBB. What we have done, we have increased VCE1. Okay, so if we makes VCE1 to VCE2, this Vy will be more than that of Vx, even further. So it becomes even more reverse bias. So it is even more reverse bias means, okay, although I am showing here between base and collector, this is between base and emitter, right? I should have drawn it differently. So that is between base and emitter. But what I try to show you that if we increase this VCE, the depletion region will increase, that will reduce the effective base width. Okay, so more and more carrier from emitter will be able to reach the collector now. So less recombination. This part again we have discussed in the last class, so I think it is much easier to see now or visualize now. The only point here is in the common base configuration, it is much easier to visualize, but here you have to remember that this Vy, if the Vy voltage is more compared to that of Vx, okay, then what we will have, it is more reverse bias, base collector junction, and more reverse bias means depletion width will increase further, okay, and that will reduce the effective base width here. So more number of carriers will be able to cross. If more number of carrier will be able to cross, then less recombination, and less recombination means less base current. Okay, so that is why I am saying the base current will decrease if we increase the collector emitter voltage, which is in contrary. You see here we showed that emitter current will increase. Okay, because we have plotted it between IE versus VBE, but emitter current increase means base current decreases, right? Because less recombination then, and that is what I have shown here, that base current will decrease if we increase the reverse bias voltage between base collector. Okay. Now what about these output characteristics? The output characteristics, let me clean this up a bit. So output characteristics is between IC versus VCE. Okay, the output characteristics here between IC versus VCE, but for different values of IB. Okay, so we have, because IB is the input current and the output current is IC, for different values of VCE, I have plotted different values of IB. Okay, here also you see IC is independent of VCE. Okay, rather it depends on the base emitter voltage, that is it depends on the base current. So if we increase the base current, okay, IC will also increase, because we know IC is equal to beta IB, right? So here also there are different modes of operation. One is active mode, where this condition needs to be there. So base emitter junction forward bias and base collector junction reverse bias. So this is your active mode or forward active mode. Okay, in case of saturation mode, which is this region here, okay, this region here, in case of saturation mode, you see your base collector junction is forward bias, and also base emitter junction is forward bias. So in this portion, base emitter junction as usual forward bias, and base collector junction is also forward bias. What about the cutoff region or cutoff mode? In this case, base emitter junction is reverse bias and base collector junction is also reverse bias. So if base emitter junction is reverse bias, then there is hardly any current or hardly any carrier passing from emitter to collector side. That represents that there is hardly any current. Okay, so we will have very little amount of current, okay, or almost no current. So that's basically my cutoff mode. And in the active mode, this condition is valid, as I said already, and in this situation, the IC is almost independent of sorry, of VCE. Okay, so here also we can say that transistor can act as a constant current source. Okay, because IC is not changing even if there is change in VCE. Okay, now This is what I have already discussed with you, but let me just go through the slide so that if there is any doubt, that will be clearer. Now, input characteristic, as I said, this is between IB and VBE for different values of VCE, and with increasing VCE, IB is going to decrease. Okay, because less chances of recombination at the base, so less IB. Okay, because the most of the carriers will be able to now cross the junction and reach from emitter to collector. And of course, this IB VB is exponential because this is base emitter junction, PN junction, and this is in forward bias. Right, so this is I have already mentioned here. Now, what about output characteristic? As I said, output characteristic is between IC versus VC for different values of IB. Okay, you remember in case of common base configuration, we have plotted similar thing, but with for different values of I. In that case, we plotted IC versus VCB for different values of I. Okay, for different values of I. But here, for different values of IB, we plotted IC versus VCE. The characteristic has three regions, as I said already: active region, saturation region, and cutoff region. In the active region, B should be forward bias and CB reverse bias, and IC almost independent of VCE. Okay, and so it is like a constant current source. But in true sense, there will be a tilt in the graph, and this is known as early effect. We will discuss the early effect in the next slide probably. Okay, so that is, there will be early voltage. That thing we will discuss in more detail. What about saturation region? As I said, in case of saturation region, B forward bias and CB also forward bias. The rule of thumb is, so in saturation region, what happens? You see, this junction is forward bias, okay, 0.7 or 0.8 volt, and this junction is also forward bias. Okay, so collector, base, and emitter. The rule of thumb is, in case of saturation region, we consider this as around 0.2 volt. So when you solve problem, you can consider this VCE as 0.2 volt when the transistor is in saturation. Okay, so both this collector base emitter junction is forward bias, and this base collector is junction is also 0.5 to 0.6 volt here will also be in forward bias. However, the point to be noted here, IC not equal to beta IB. In the saturation region, IC not equal to beta IB. So if you manage to see that IC not equal to beta IB, and you can check that VCE 0.2 volt, you can say, or close to 0.2 volt, you can say that it is in the transistor is in the saturation region. Okay, and in saturation region, of course, this current will quickly go to zero. Okay, you see the current is quickly going to zero. Okay, in the saturation region. What about cutoff region? Cutoff region, base emitter is reverse bias and collector base is also reverse bias. So no hardly any flow of carrier between emitter and collector. So whatever we will get is a collector base reverse bias. They have a very small amount of current or almost no current. Okay. Now this is IV characteristics of the common emitter configuration of BJT. Now let's discuss that early effect situation. We have exaggerated the IV characteristics here in this plot. You see IC versus VCE, and I have plotted for different values of VBE. I have zoomed in this region close to this region here. Okay, and I have plotted different values of VBE, and you see, as I mentioned, it is not exactly flat, but these curves are bit tilted. So IC is not entirely independent of VCE. Okay, this is obvious. This is because as I mentioned to you earlier, that if you increase your VCE, your reverse bias is going to increase, and if there is increase in reverse bias, if there is increase in reverse bias, this effective base width, so if this is base, this is collector, if you increases VCE, this effective base width going to decrease, and if it is going to decrease, IC is going to increase. So you see IC is not exactly flat like this, okay, rather it is little bit tilted, okay, and if you extrapolate this tilt, then it will ultimately converge to a voltage, okay, which is known as early voltage, which usually represents as minus VA, okay. So if you extrapolate these current current voltage plots, it will ultimately cross this collector emitter axis, negative axis, to a point that particular voltage is usually designated as VA or minus VA, that is basically early voltage. And this effect, which shows that this effective base width decreases and collector current increases with increase in VCE or with increase in reverse bias, this particular effect is known as early effect, okay. So early effect modifies IV characteristics in the active mode. Now you see IC can be usually we write IC is equal to IS exponential VB over VT, but here we have added one additional term. We multiplied one additional term, which is 1 plus VCE over VA. This is because of this early effect. Now we can find out the corresponding resistance by del IC over del VCE, that is the change in current with change in collector emitter voltage at a constant value of VBE. And it is possible to show, if you do this, if you differentiate this IC with respect to VCE at a particular value of VBE, you will get that R naught nearly equal to VA over IC. So that's basically your output resistance, okay. And if we consider VA is infinity, okay, if this is flat like these lines I have drawn, then R naught tends to be infinity, right? Now, so this is what I have mentioned here in these lines. Increase in VCE increases the reverse bias collector based junction voltage, and thus depletion width increases. This reduces the effective base width, as I have said several times before, and this in turn increases IE, hence IC, okay. So when the curve are extrapolated to zero current, so here I have extrapolated to zero current here, so here IC is 0, they meet a point on the negative voltage axis, and at VC is, that is the early voltage, okay. Now next thing we are going to discuss is DC analysis of transistor circuits. DC analysis is very important, because then it will because the concept of DC analysis will help us to design a transistor circuit. So we will be able to know what should be the value of VBB and VCC, and what should be the value of RB and RC, okay, which we need to use to take transistor to a particular region, whether it is saturation, whether it is cutoff, or whether it is forward active region. So DC analysis, concept of DC analysis in that way is very important, because it can help us to design the circuit properly according to our requirement. Now you see, this is a common emitter circuit with NPN transistor, as we have already seen this circuit, okay. We can if you see carefully, these subscripts use subscripts of BJT terminal RC, RB, etc. So RB means this resistor is connected to base, okay. RC means this resistor is connected to collector. If we use any resistor here in the emitter side, okay, then we usually name it as RE. So this is the usual concept or usual nomenclature, the way we name them, okay. And DC voltage, or the way we represent them, and DC voltages, if you see, double subscripts of the BJT terminal, okay. So you see, VCC means this voltage is connected to collector, and VBB means this voltage is connected to base, okay. Now we can represent the circuit in this fashion also. You see, VBB here, VCC here, there is RC, RB, and collector is connected to RC, collector is connected to base is connected to RB, and emitter is grounded. Okay, this is the way you can also represent. Now the DC, so we can replace this transistor with this simplistic model. What is this model is saying? You see, base emitter junction, we said forward bias, so that is like nearly 0.7 volt for a silicon transistor. Okay, if that is the case, we can replace this junction as a diode. Okay, and we have written the voltage across diode is VBE on, which is close to say 0.7 volt. Okay, and what about the collector emitter junction? This collector emitter junction can be replaced by a constant current source, which is beta IB. IC is equal to beta IB, right? And you see here, this is as we mentioned, this is constant current source here, right? In the forward active region or active mode, this is transistor can be assumed as a constant current source. So that is exactly what we have done here. We have designated this collector emitter junction, okay, as or we replace collector emitter with a not collector emitter junction we represents collector emitter as a constant current source which depends on IB. Okay, so beta IB. So this is your collector terminal, this is your base terminal, and this is your emitter terminal. Emitter I have grounded according to this circuit. So this base terminal through this resistor RB is connected to this VBB supply voltage, and this constant current source, you see the direction of the current. Obviously current is entering from the collector side, current is entering from the base side, and current is going out from the emitter side. So you see the direction of the currents, and so here the current direction you can see, and there is RC resistance and VCC voltage source. Now if we can write the two equations depending on the input and output loop. If you write the KVL equation for this input loop, we can write IB RB plus VBE or VBE on whatever is equal to VBB. So this is the if we write the KVL for this input loop, this is the KVL equation. What about the output loop? Output loop also you can write IC RC. Okay, so this is your IC RC plus VCE, voltage drop between collector and emitter, that is VCE, right? So ICRC, that is the voltage drop here, because IC current is flowing. So ICRC is the voltage drop across the resistor, and VCE is the voltage drop in between collector and emitter. Okay, this is equal to VCC, right? So this is the output loop KVL equation, this is the input loop KVL equation, right? So we can write these two equations to solve the operating point of the solve different values of IC and IB and VC, etc. Okay, so you see IB is you can write IB, okay, and you can also write IC from these equations. So IB will be this and IC will be this. Here we are not considering the reverse leakage current, okay, and also we are not considering early effect. And we have, as I mentioned to you already, assuming BE junction is forward bias, so voltage drop in the BE junction is VBE on, okay, and when the transistor is biased in the forward active mode, we can consider that the collector current is represented as a dependent current source, okay, and that is function of the function of base current, which is beta IB. So IC is equal to beta IB, and so you see we can find out IB, IC, VCE, etc. And here implicitly we are assuming obviously that VCE is more than VBE, okay, that is why this base collector junction is reverse bias, right? So VCE is more than, so VCE is more than VBE, okay, or VBE on. So this represents this base collector junction is reverse bias, right? and we can find out the power dissipated in the transistor. The power is basically current into voltage. Okay, so in the B junction this is the power dissipation, and in the collector we can consider collector current IC VCE. Okay, so these two power, if you add, then it is the total power. In fact, this power is nearly equal to IC VCE, because IC is much larger than that of IB, beta times larger than IB. Okay, IC. So this although total power is summation of these two factor, okay, or these two values, but it is nearly equal to IC VCE, because IB VBE on will be much less than IC VCE. Okay, now so there is a way to find out this IB, IC and VCE. This is known as load line. So how we can find out those IB, IC and VCE value? Let's discuss that. So from this, so we know this is our IB VBE, okay, that is exponentially increasing for a particular value of VCE. Now if we plot this in the same if we plot this equation on the same curve, okay, then we will get this straight line. How? So you see at this point here, let me change the color. So at this point here, so VB is equal to here you see VB is equal to 0, okay, because VB is 0 here on this y axis. So if that is the case, if this is 0, okay, so this IB equal to VBB over RB, that is I have written here. What about this point here? This point is IB equal to 0, because it is on the x axis. If IB is equal to 0, then we can say VBE is equal to VBB over RB. Okay, IB is equal to 0 means VBE is equal to VBB, sorry, VBE is equal to VBB, right? So you see that we can draw a straight line, and this straight line crossing the exponential plot in this point, which is known as Q point. Okay, so this is basically your IBQ, base current at the Q point, and this is equal to VBEQ, the base emitter voltage at the Q point. So Q point is very important, because Q point will tell you at what current and voltage this transistor is in, because you have used RB, RC, etc. Those define the current. So we have to make sure, we have to know that this is the IB VB is following this exponential plot, right? But on this exponential plot, where this transistor is sitting, that we need to find out. That will basically give us the Q point, which can be figured out by getting the solution this way, where the load line is crossing the this exponential plot. Okay, and that basically designate the IBQ and VBEQ. We can use the same trick and draw the load line in the output on top of the output characteristics. So here you see this is the output KVL equation, okay, and we can assume that VC is equal to 0, that is on the y axis. So if VC is equal to 0, then IC is equal to VCC over RC, that is I have written, this is this point here. Okay, now what about in the x axis? When it is on the x axis, IC is equal to 0, so we can write VCC is equal to VCE is equal to VCC. Okay, VCE is equal to VCC. So this straight line here is basically your load line, and we know IBQ from the input plot, right? Input exponential plot and load line. The solution is giving us IBQ. So if IBQ is known, say for example this is my IBQ point. Okay, so say 40 microamp of that base current is giving me IBQ. So if that is the IBQ, So then this is the Q point on the output axis. So corresponding this is my ICQ, and corresponding this is my VCEQ. Okay, so this is again Q point as far as the output characteristics is concerned. So this is how we can find out IBQ, IBQ, ICQ and VCEQ, and value of these is quotient value or Q value of these these parameters is very important, because this will then tell me that whether this is in the active region or forward active region, or this is in the saturation region, or this is in the cutoff region. So we depending on the application, if it is the amplifier application, we need to keep the transistor in the forward active region, and if it is acting as a switch, we have to keep the transistor in the saturation or in the cutoff region, right? So the last thing I would like to discuss today is how we can use this transistor as a switch. Okay, so right, so if we increase if Vi is less than 0.7 volt, okay, and if this is my V out, okay, so I am using the common emitter configuration again, and this is NPN BJT, okay, this is my emitter terminal because the arrow is there, and this is my base terminal, and that is my collector terminal. Okay, so you see this V out, if Vi is less than 0.7 volt, okay, so if Vi is such that it is less than 0.7 volt, that is less than VBE on, then you see this transistor is off. Okay, BJT off. Now if BJT is off, we can redraw this circuit in this fashion, because BJT is off, you see. So if BJT is off, there is hardly any current, there is no current. Okay, and if there is no current, okay, this entire voltage VCC will be at V out. So we can write V out equal to VCC, because there is no current flowing through the transistor, it is like off, and so there is no voltage drop across RC. Okay, so if we measure voltage here, it is like a voltage divider circuit where we have RC here and as if infinite resistance, because this transistor is off. Okay, so entire voltage is on this across this infinite resistance, so we will get V out equal to VCC, right? What about if Vi is okay more than 0.7 volt, very large, say close to, I don't know, close to say 0.8 volt or so, okay, in such a way that this transistor is in saturation. In other words, in that case, say this is my VCE is equal to 0.2 volt. You remember we considered, we told that the rule of thumb is when the transistor is in saturation, this VCE will be 0.2 volt, okay, close to 0.2 volt, and if that is the case, then the entire voltage will be across this RC, right? So there will be lots of current, lots of IC, okay, and we can then draw this circuit in this fashion where there is this switch is as if on, only there is a voltage drop of 0.2 volt. So rest of the voltage will be across RC, that is like VCC minus 0.2. So if VCC is 5 volt, then RC will have 4.8 volt, okay, across it. So if I measure V out, V out will be very less, that is V out will be close to 0.2 volt. Okay, and here BJT is on. So you see, or the switch is on. So you see BJT in this configuration acting as a switch. So if we can take, so if I plot those output characteristic IC versus VCE, so for different values of IB, okay, so you see when there is hardly any current, then transistor is in cutoff. Okay, so BJT is off and V out equal to VCC. So the entire voltage, if we measure at the V out, will be equal to VCC. Whereas when the transistor is heavily on, okay, and transistor is somewhere here, okay, so that is like 0.2 volt, VC 0.2 volt. Okay, in that case the entire voltage will be across RC, and if I measure V out, we will get close to 0.2 volt. That is as if it is like a switch, because you know, in case of switch, when the switch is off, there is no current through the switch, entire voltage will be across the switch, and when the switch is on, all the current will be through that switch, and voltage drop across the switch is very small. Okay, in ideal case the voltage drop should be 0 volt. Here it is close to 0.2 volt. So you see, so this way transistor can act as a switch, or BJT can act as a switch. We have to take the BJT, we have to bias the transistor. What is biasing? We will discuss that. We have already discussed forward and reverse bias, but how we can get proper biasing in the transistor, that we will discuss in the next class. But what I want to mention is that if we take transistor into saturation region, it will act as switch will be on, and if we take it in the cutoff region, then the switch will be off. Okay, so with this we are closing the class today. So thank you for very much for your attention, and bye for now.